Now let's talk about switches and hubs in an Ethernet network. Now, if I have four computers, A, B, C, and D, and I want to connect them physically, I'm going to connect them through a hub, lowercase h, in an Ethernet network. Okay? So what that's going to look like is I've got a device here in the middle, and all of my other devices are going to connect to that. Okay. Now this is the topology of an Ethernet network. It's a star bus topology. It looks like a star, but it actually functions as a bus because inside of this box all of these lines are connected to the same line. Okay. Now in older Ethernet networks, this device was a capital H hub. You'll notice that I'm differentiating between a lowercase h hub and a capital H hub. A lowercase h hub is just a generic term to talk about a device that connects a group of computers together. A capital H hub is a specific type of device. Now these were the original hubs of Ethernet. They would allow any conversation coming into the hub to be replicated across all of the other lines leaving the hub so that all of these computers could hear the conversation. And that made sense. So if I've got four computers and A wants to talk to D, A is going to go ahead and send out a frame with D's MAC address. It's going to reach this device. Now this is an electronic repeater, so it's going to send that frame out to C and B and D. Now when B receives it, it's going to look at the MAC address and say, hey, that's not my MAC address, and it's just going to drop the frame. C is going to do the same thing. It's going to say, that's not my MAC address, it's going to drop the frame. D is going to get the message, and it's going to go ahead and say, hey, that is my MAC address, and it will receive it. And for four computers, this isn't too bad. C and B might have to drop a variety of packets that A and D are passing back and forth, and same thing. C and B might be having a conversation that A and D have to ignore. But for four computers, this kind of makes sense. Now the issue comes up when we start to add more computers. But even in this simple configuration of four, we do have the problem of what we call collisions. So Ethernet networks are what are called CSMA-CD networks. CSMA-CD networks. What this stands for is Carrier Sense Multiple Access Collision Detection. So the carrier sense part of this, the CS, is that all these computers can sense whether or not a line is in use or not. So if somebody else, if C is talking to B, B knows that somebody is sending information in. So they can sense whether or not a line is being used, if information is being sent. MA, or the multiple access, means that each of these devices have equal access to the network. In some of the other networking topologies or the old technologies like the token ring network, only certain computers could talk on a network at any given time. Multiple access says everyone has equal rights to talk on the network at any point in time. Collision detection is a special thing that allows each of these computers to detect when two conversations reach a computer at the same time. So for example, let's say that A and D want to send something to computer B. They both are sensing the line with that carrier sense, and they notice that nobody is talking. Multiple access means they both have equal access, so they don't have to wait for anyone to stop talking, or they don't have to wait for any particular time in order to start talking. So let's just say that they begin talking at exactly the same time. So A and D both start sending information to B. Well, both A's frame coming to the hub and D's frame coming to the hub are going to be replicated over to B at the same time, because the hub is not smart enough to separate out conversations. And so the A frame and the D frame are going to collide and come into B at the same time. And that's where the collision detection comes in. When that happens, B is going to be confused. But A and D, because they can now sense the conversation going on, they're going to detect that collision. And when they detect the collision, they're both going to stop transmitting. There's no sense in continuing because B isn't going to receive the proper information. It's going to be all muddled. So A and D are going to stop transmitting because they've detected a collision. They're going to wait a random amount of time, and then they're going to try and send information again using that carrier sense to see if anybody else is talking, and if nobody is, with multiple access, they'll be allowed to transmit that information. So let's say that A waits 1 second and D waits 2 seconds. After a second has passed, A will go ahead and start their conversation with B. D will wait until that conversation is done, and then D will go ahead and transmit their information to B. And so with a hub, we consider all of the computers connected to the hub in a collision domain, because any of these computers could end up sending information that collides with another computer. Now with 4 computers, a collision might happen once an hour or once a day. It's not going to be fairly frequent, so it's not going to disrupt communication. But realize as this network gets larger and larger and larger, think of corporate networks that might have hundreds of computers on the same network or even thousands of computers on the same network, and now all of a sudden you're going to have collisions every second. And each of those collisions causes everybody on the network to stop, wait a random amount of time, and then start talking again. With gigabit networks in today's world, thousands of devices, the latency that would create, the amount of downtime that you'd have waiting for people to stop talking would just be unmanageable. And so that's why we invented switches. This hub network design works to a point, but it's somewhat difficult. And so what a switch does, let's upgrade this guy to a switch. A switch is going to remember which port these computers are connected to. Okay, so let's say that my switch has 4 ports on it. So it's going to say 1, 2, 3, 4. It's going to watch for traffic on each of those ports, and as it sees traffic coming from A on port 1, it's going to remember, aha, computer A is on port 1. And as it sees traffic coming from B on port 2, it's going to say, aha, computer B is on port 2, and that must be a path to computer B, computer D, computer C, etc. Okay. So as it builds that table and new information comes in, so now let's say computer A wants to send a frame to computer D. A is going to send it to the switch. Unlike the hub, which would replicate that packet across all of those different wires, the switch is going to look up in its source address table which port computer D's MAC address is on. And if it's seen traffic from D come in on port 3, it's going to know that port 3 is a path to get to computer D, so it's going to go ahead and forward that frame to computer D. Now notice it only forwards it to computer D, not to C and not to B, which means that C and B can have a conversation at the same time that A and D are having a conversation, and none of the packets collide. There's no issues with those two conversations going on at the same time. Now, if a switch doesn't know where a computer is, let's say that computer C over here has been silent this whole time, so the switch doesn't know where computer C is. A sends a frame to computer C, it's going to come to the switch doesn't know where it is, so it's going to revert back to that hub mode, and it's going to send it across all of these different paths until C responds to that frame, makes it to the switch, C's sending back to A, so the switch knows where A is, so it's going to go from C to A. Now the switch has seen traffic from C, and it can remember in its source address table that port 4 is the port that C is connected to. Okay, so that's the path to C. And so because of this, the switch now sitting in between all of these devices and connecting these conversations, it also has the ability to buffer frames. So if something is already being sent to B, it can wait for a moment and then send that over to B. The switch effectively separates each individual port into its own collision domain. So in this setup, rather than having 4 computers in the collision domain, which we would with a hub, we now only have 1 computer in each collision domain. The Address Resolution Protocol, or ARP, is the way that a computer determines the MAC address of another computer on an Ethernet network. So for an example here, we have a network with 4 computers, A, B, C, and D. They're all connected to a switch, and that switch is brand new, just turned on, so it doesn't actually know where most of these computers are. So it's going to be watching for traffic from each of these computers in order to build its source address table, much like we talked about in the last video. Each of these computers has a MAC address. So computer A, for example, might have AA, BB, CC, 01, 02, 14. Okay? Some MAC address. Computer C might have a similar MAC address, but remember, MAC addresses are globally unique. And so it's got a different MAC address than computer A. Now in Ethernet communications, all Ethernet frames have to have a source MAC address and a destination MAC address. So if A wants to talk to C, A needs to put in their MAC address as the source MAC address and this MAC address as the destination MAC address. Now the problem comes when A is talking to C for the first time. A has no idea what computer C's MAC address is. So we need to use this address resolution protocol to figure out what computer C's MAC address is so that they can have a conversation. So the way that this is going to work is A is going to send out an ARP frame. That ARP frame is going to be sent to the broadcast MAC address. The broadcast MAC address is a special MAC address that is all F's. Okay, since these are hexadecimal characters, F is the last one. 1, 2, 3, 4, 5, one more, 6. So this is the broadcast MAC address. F is the last digit in hexadecimal, so FF, this would be the last MAC address in existence, and it's reserved as the broadcast MAC address. This MAC address is essentially used to reference every computer in the world. Okay. So when computer A wants to figure out what computer C's MAC address is, computer A is going to create an address resolution protocol frame, putting its MAC address as the source and all F's as the destination MAC address, and then it's going to put some information about computer C, whether that's a host name or an IP address or some piece of information that we can identify C, and it's essentially going to broadcast out to the network, hey, who is C? Tell me at my MAC address. So A sends out the frame and it comes to the switch. Now the switch is going to notice the broadcast MAC address and it's going to default to hub mode and send it out to all other computers because it's a broadcast message. So B is going to get it and look at that and say, oh hey, that's the broadcast, I should look into that. It's going to open it up and it's going to say, are you C? And B is going to say, nope, I'm not C, and it's going to drop that frame. Same thing with D. D is going to look at that broadcast MAC address, say, oh, that might be for me, open it up, say, nope, I'm not C, and then drop it. C is also going to get it, see that broadcast MAC address, open it up and say, oh yes, I am computer C. And because A included their MAC address as the source MAC address, C can then create a frame responding to that ARP request and say, hey, I am C, here is my MAC address, and he can go ahead and put in computer A's MAC address as the destination. So C sends that frame back to the switch. The switch is going to look at that destination MAC address and know that computer A is on port 1, so it's going to send it out on port 1 only. A receives that response, and now A knows C's MAC address, and because of the ARP request, C also knows A's MAC address. And now they can have a conversation back and forth because they both know the MAC address.